So today I'm going to talk about a recent work called Beyond Lazy Training for Over-parametrized Tensor Decomposition. So this is based on joint work with my students Xiang Wang and Chen Wei Wu, and also Jason Li and Tang Yu Ma. Okay, so I guess before I tell you what is the actual problem we are looking at and our results, I'd like to first talk about why this is related to low rank models. So think about simple matrix problems. So suppose we are looking for a low rank matrix M. One of the typical way to do that is actually to express M as a factorization form. So you write M as U times V transpose, where U, let's say M is a D by D matrix, then U is going to be a D by R matrix, and V is going to be also a V transpose is going to be an R by D matrix, right? And by controlling this size of the matrices U and V, you can control the rank of U times V transpose. However, that's only one way to achieve low rankness. And recently, a series of work has shown that even when this size of the matrices U and V are much larger than the rank of M or the desired rank of the solution M, you can still run gradient descent for many problems, and gradient descent will still find a low rank solution. So there's a lot of papers on this topic, and some of the authors are also going to be in this mini-symposium. So this phenomena is called implicit bias or implicit regularization of gradient descent. So it shows us that the low rank properties may arise even when we don't specifically enforce low rank properties for in our parametrization. So in this talk, what we're going to talk about is whether the same phenomena would happen for over-parametrized tensor models. Can gradient descent on over-parametrized tensor models leverage some low rank structure in tensors? So this is an interesting question, mostly because there are two different regimes of over-parametrization. This is mostly referring to over-parametrization of neural networks, but the same categorization would also apply to tensor decomposition problems. So the first regime of over-parametrization that's now well known is called neural tangent kernel. So in neural tangent kernel regime, you will start with some random initialization, and implication of neural tangent kernel regime is that these neurons will actually not move too much. So if you use this neural tangent kernel to fit either a matrix or a tensor, then even if your original matrix or tensor is low rank, the components that you have in your neural tangent, the components that you find will not actually be low rank. So in some sense, neural tangent kernel would not be able to leverage the low rank structure. On the other hand, there's a different limit to very wide neural networks called the mean field regime. So this is in general harder to analyze because one benefit of neural tangent kernel is that we have very good convergence results for neural tangent kernels, and we have explicitly like how wide your neural network needs to be in order for it to enter the neural tangent kernel regime. For mean field regime, it's harder to analyze, but it certainly allows the neurons to move much farther. And if you are in this regime and you are trying to fit some low rank matrices or low rank tensors, it can the components you find can potentially be low rank. So in this work, we are going to try to analyze a regime that's similar to mean field regime for tensor decompositions. So more precisely, we work on the tensor CP decomposition problem. So suppose we are given a T star, which is a rank R tensor. So T star is equal to summation I from 1 to R, Ci star Ui star tensor L. So it's a Lth order tensor. we are looking at symmetric tensor for simplicity, but it could actually generalize to asymmetric tensors. And so assume that UIs are of D dimensions and R. We think of the rank of the tensor R, we think of as something that's smaller, that's much smaller than D. So given this tensor T star, the CP decomposition problem asks you to find a decomposition that has a similar form, right? You want to write T star as T, which is the summation I from 1 to R, Ci UI tensor L. And we are going to try to solve this problem by using a naive algorithm. So the naive algorithm is just going to run gradient descent on the simple objective of T star minus T Frobenius norm squared. Your Frobenius norm for tensor is just you will vectorize the tensor and take the L to norm. Okay, so if you run this naive algorithm, it wouldn't work. Okay, so the naive algorithm fails for many different reasons. So first of all, of course, we shouldn't expect the naive algorithm to work because computing the rank of a tensor is NP-hard. But the problem is even more severe than that because gradient descent actually will stuck even when the tensor is orthogonally decomposable, which means the components UI stars are actually orthogonal to each other. Okay, so the orthogonal decomposable tensors are like a particular class of tractable tensors. There are many efficient algorithms to do tensor decomposition for them, but gradient descent in this form will also get stuck fairly frequently. In order to address that problem, one thing you can do is actually to allow over-parametrization. And over-parametrization in this case means that even though our ground truth tensor T star has rank R, I'm allowing the tensor that I learned T to have M components, where M is actually much larger than R. Okay, and empirically, for orthogonal tensors, if you do over-parametrization, you often will not get stuck. So the new objective that we are going to analyze is going to try to minimize, again, the Frobenius norm difference between T star and T. But now T star is a rank R tensor, but T has M components and M is much larger than R. The question that we are interested in is how large does M need to be in order for gradient descent to be able to optimize this objective? And we want this bound for M to depend on R, which is the rank of T star. If we are able to allow M to depend on R, but not very strongly on the M in dimension D, that suggests that this algorithm is able to leverage some of the low rank structure. So what we can show is when M is so R to the 2.5 L, where L is the order of the tensor. Throughout the talk, you should think of L as a constant, let's say something like 4. So for M, that's R to some constant power or some. So these powers are very likely to be loose, but that's what we were able to prove. When M is poly R over epsilon times some log factor on the M in dimension D, a variant of gradient descent can optimize this objective function star with an accuracy of epsilon in polynomial number of iterations. So basically, gradient descent can indeed find the low rank structure, leverage the low rank structure of the tensor. In this result, we do not need to assume any structure on the ground truth tensor T star. It just needs to be any rank R tensor. And this problem itself of writing a tensor T star as a different tensor with higher rank, with a different decomposition with higher rank, is actually not very difficult. So solving this problem itself is not what we are interested in. In order to solve that problem, you can actually just first try to get the span of the UI stars by looking at any slice of the tensor. And then when you project everything to the span, you get a R dimensional tensor, you get a R by R by R, R to the power L size tensor. And you can always write any R to the L tensor using roughly order R to the L minus 1 components. So, and our number of components is certainly larger than that. So there's room to improve there. But what's surprising about the result is we don't need to run the spectral algorithm. We can actually just directly run an algorithm that's very similar to gradient descent. And the algorithm will automatically pick up this low rank structure. We also have a related work later where we show that polynomial over-parametrization will be able to find the tensor exactly when the tensor is orthogonally decomposable. So why are we interested in running gradient descent here? Mostly because, well, first of all, gradient descent is a natural and scalable algorithm. Properties for analyzing gradient descent can often be useful for analyzing other algorithms. But more importantly, this tensor decomposition problem that we look at is closely related to training a two-layer neural network, and the stochastic gradient descent is the default algorithm for training neural networks. Let me first talk about this relationship between two-layer neural network and tensor decomposition, and after that, I will give you some ideas of the proof. So for a two-layer neural network, let's assume that the hidden layer H is just a nonlinear function sigma applied to some matrix U times X. We're going to assume the rows of U are of unit norm. This is without loss of generality because usually a neural network is going to be too homogeneous, or a two-layer neural network is going to be homogeneous. So the output is just some linear function on top of the hidden representation. Suppose we generate the data by first sampling X from a Gaussian distribution and then generating Y according to a ground truth neural network. The goal is to find a neural network that has the same output. So if you think about this objective, when the rows of U star and U are of unit norm, then the objective for the two-layer neural network is equivalent to this form, where it is a summation of many different terms, and the else term is a difference between the else moment for the true parameters minus the else moment for the current parameters. And we care about the probability norm squared difference between them. And the coefficient in front of this else term is going to be the else Hermite coefficient for the activation function. And for the standard activation function, the ReLU activation function, the non-zero Hermite coefficient include 1, 2, and all the other even order terms. Okay, so because of that, we can always view this neural network problem as a summation of tensor problems. And what we are going to do now is to focus on one of the tensor problems. Okay, so there are many difficulties in analyzing gradient descent in this over-parametrized regime. Mostly there are three difficulties. One is lazy training, or neural tangent kernel regime will actually fail fail to leverage the low rank structure. And then another difficulty is that the 0 point is actually a very high order saddle point for the standard objective. And further, even if we deal with this high order saddle point, there are actually many local minimum that's bounded away from 0. Let's first look at some of these difficulties, and I will briefly talk about what we do in our algorithm or analysis in order to solve these problems. So first, the lazy training fails. So the lazy training regime, as I mentioned, is just another name for neural tangent kernel. The lazy training regime would require M to be omega of d to the L minus 1 components in order to optimize the objective with a constant accuracy, even when R is equal to 1, right? Even if the ground truth tensor is of rank 1, if you are running a neural tangent kernel regime, if you are doing the initialization in the neural tangent kernel regime, it would require a very large number of components. In particular, it depends polynomially on D, and it does not decrease even when the rank of the ground truth tensor is only 1. So intuitively, the reason why this is the case is in lazy training, your components cannot move by too far, right? You basically need to stay where you are. In lazy training, if you have m random components, they will represent a subspace of m times d dimensions. But we know a tensor of dimension d of order L has d to the L parameters. So in order to fit all of these d to the L parameters, we need m to be as large as d to the L minus 1. So we cannot use the lazy training regime for this optimizing the over-parametrized tensor model. So in order to fix this issue, we are going to avoid lazy training by using a very small initialization. One way you can enter the lazy training regime is to use a large enough initialization when you are initializing all the components. To avoid doing that, we use a very, very small initialization for each of the components. So the next problem is that the 0 point is actually a high order saddle point. So for a single component, which has the form Ci times Ui tensor to the L, the scale of Ci, so there are some redundancies between Ci and Ui, right? So the scale of Ci can go into the scale of Ui and vice versa. One way to get rid of this redundancy is just to write it as Ai times Ui tensor L, where Ai is just fixed and it's either +1 or -1. But if we use this very natural parameterization, what happens is that the 0 point is going to be an order L saddle point. And because it is an order L saddle point, if you are near 0, the gradient is going to be proportional to the norm of Ui to the power L minus 1. And of course, as we mentioned, we use a very small initialization. If we use a very small initialization, norm of Ui to the L minus 1, it's going to be very, very small, and it would take too long to train. So in order to fix that, we actually change the parameterization of the components as Ai times Ci to the power L minus 2 times Ui tensor L, and we fix Ci to be equal to 1 over norm of Ui. As you can see in this parameterization is actually too homogeneous in Ui, right? If I scale Ui by a factor of lambda, then this component scales by a factor of lambda squared. So it is too homogeneous instead of L homogeneous as the standard parameterization. And because it is too homogeneous, and too homogeneous, of course, corresponds to L equals to 2 in previous settings, and L equals to 2 is in the matrix setting. Since the model is somewhat similar to matrices, if we run a matrix power method, right, then the small components will be able to grow exponentially. If you run the power method, you keep multiplying a vector x by the same matrix, then the top eigenvector of this, the top eigendirection is going to grow exponentially. So by using a very similar to homogeneous parameterization, we are also hoping that the components are going to be able to grow exponentially, which allow us to use a very small initialization. So finally, we also show that there are local minima that spotted away from 0. So assume some basic requirements for the parameters. There exists a symmetric ground truth tensor with low rank, such that a local minimum with function value that's bounded away from 0 exists, while the global minimum has function value 0. We can construct these local minimum for fairly general models. The requirements are not very strong. So we need a way to avoid getting into these local minimum. So there are two possibilities. One is maybe in the analysis, you can try to prove very carefully that you will never get around these local minimum. But you can also just modify your algorithm to make sure that you can escape from local minimum even if you are stuck, or even if gradient descent will be stuck. So here we actually take the second route, as we don't actually know how to avoid this type of local minimum. So in order to escape from these local minima, what we do is we will initialize a small fraction of components randomly every once in a while. So if you get stuck, you have a chance to escape from this local minimum by this reinitialization process. With all the modifications, here's going to be our algorithm. Of course, the algorithm looks complicated, but don't look at this algorithm. So basically, the first part is just saying we set the components according to this two homogeneous parameterization, and we use a small initialization. As we talked about, the two homogeneous parameterization is used to deal with the fact that 0 is a high order saddle point, and small initialization is there to avoid lazy training regime. So for each epoch, we will firstly randomly do the random reinitialization step in order to try to escape from a local minimum. And then we will run gradient descent, and we will fix Ci to be equal to 1 or norm of Ui. This is again for the two homogeneous parameterization. There is, so that's basically the algorithm, but there is an additional step which says if the norm of the component crosses some threshold for the first time, we will change the value of Ci, which we call the scalar mode switch. So we are not quite sure if this step is necessary in practice. There's no major obstacle of why we need to have that, but having that is what we know how to make the proof go through. So for the remainder of the talk, I'm just going to give some simple ideas in the proof. So we will first try to prove that this gradient descent procedure indeed will leverage the low rank property. In particular, we'll show that the iterates will remain very close to the correct subspace, where the correct subspace is a subspace that's spanned by all the ground truth tensor components. Once we make sure that the iterates remain close to the correct subspace, we can hope that everything to only depend on the rank of the ground truth tensor instead of the ambient dimension D. And after that, we analyze how one can escape the local minimum by the random reinitialization. And then we will show how this reinitialization can actually get, so this has two steps. We will first show that if you do the random reinitialization, it will have a non-trivial correlation with the residual tensor. And then we will show how this initial correlation can be amplified by something that's very similar to a tensor power method. Okay, so the first step of the proof is to show that the iterates will remain close to the correct subspace. Again, by the correct subspace, we mean the span of the ground truth components. So we will use S to denote the correct subspace, and it is just the span of U1 star, U2 star, all the way to UR stars. Remember that the algorithm doesn't know this space. So this space S is only used in the analysis. So intuitively, we want all the components UI to be in S. If, the UI stars are already in S. If all the components UI are also in S, then we can view both tensors T and T star as a R to the L tensor instead of a D to the L tensor. And if both of them are R to the L tensors, then we should expect most of the things to depend on R instead of polynomially on D. So we show that this is indeed the case when running the modified gradient descent algorithm. The total norm in the orthogonal subspace of S will not increase. Okay, so this fact, along with the fact that we are using a very small initialization, so initially the total norm in the orthogonal subspace of S is very small. Just by combining these two, we can guarantee that both T and T star are mostly in the subspace tensor itself L times. This lemma sounds clear, but it's surprisingly not trivial if we don't do our reparameterizations. A lot of our reparameterizations are there in order to guarantee this lemma to be true. Okay, so now we have guaranteed that both T and T star are close to the correct subspace. We're going to talk about how you can try to escape local minimum by taking a random correlation. So here we actually use a very basic anti-concentration inequality. So we show that this is actually a direct corollary of some anti-concentration. So when both T and T star are in the good subspace, if you also take a random vector U, which is also in the good subspace with unit norm, then the correlation of U tensor L with the residual T minus T star is going to be at least 1 over R to the L over 2. It's going to be at least this with some constant probability. So because we have this good correlation, we can expect, even if we are currently stuck at some local optimal solution, once we reinitialize, there will be a component that's actually correlated with the residual direction. And if we increase the norm of this direction, then the residual is actually going to decrease. So the question is, why would gradient descent do that? Why would gradient descent increase the norm of this direction very quickly? So for that, we use an analysis based on tensor power method. So if a vector U satisfies T minus T star inner product with U tensor L is at least 1 over C, then we show that the corresponding component doubles its norm in roughly C iterations. So here we are still assuming that U is actually a unit vector. So this applies to, when we apply this to a component, this is what's inside the correlation is a normalized version of U tensor to the L. So basically this tells us that as long as the correlation is large, we can hope that the corresponding component will grow very quickly in terms of its norm. And the fact that this growth is exponential uses the two homogeneous reparameterization. If it's L homogeneous instead of 2 homogeneous for L bigger than 2, then the growth is not going to be exponential at the beginning. However, there's a huge problem here because the anti-concentration result only guarantees if U is actually in the good subspace, then there is a very good correlation. But when the algorithm is doing the reinitialization step, the algorithm does not know the good subspace. So the algorithm is going to pick a random vector in the entire D-dimensional space. And because both T and T star are in the good subspace, the correlation with a random vector in this D-dimensional space is not going to be very large. In fact, it's going to have some large D factors there. So the initial correlation C is not 1 over poly R, but instead 1 over poly D. And this will cause a lot of problems in the analysis. It will make the algorithm much slower, and it will also break other parts of the analysis. So the solution to that is we actually use a much larger learning rate at initialization. So intuitively, initially we use a much larger learning rate in order for the components that's within the R-dimensional space to grow very fast. And once the component in the good subspace is large enough, we will switch back to a smaller learning rate, and it's okay because we already have a good enough correlation with T minus T star. So this is the scalar mode switch step that I was talking about when we were looking at the algorithm. So that's why it's actually necessary for our proof. So in this result, what we show is variant of gradient descent can actually automatically discover low rank structure in the target tensor. In particular, if your target tensor is of constant rank, then you can also fit that tensor very efficiently. Well, this is not going to be true if you are using a neural tangent kernel regime or the lazy training regime. So this shows that over-parametrization can potentially help in tensor CP decomposition. But of course, there are many open problems. The most immediate open problem is how can we generalize the result to a two-layer ReLU network, which is partly the motivation of our work. The difference is that in the two-layer ReLU network, as we talked about, its objective is equivalent to a sum of tensors of different orders. And one part of our proof, which guarantees that the norm in the orthogonal subspace in the bad directions decrease, that proof actually is kind of sensitive to this modification, and that's why we are not able to generalize it directly to two-layer ReLU networks. And perhaps a more interesting open problem is, in this case, we show that gradient descent can discover a low rank structure and make some use of the low rank structure. But can we hope gradient descent to discover any other structure instead of just a low rankness of the ground truth components? Thanks. And any questions?
Thank you very much, Rong. Are there any questions? I have a quick question. So you mentioned that the exponent that you have for the over-parametrization is not optimized.
That's right.
Do you have any guess of what do you think that will be the optimal exponent? Or
right. Let me try to go back to that. Let me go back to that result slide. Yeah, so here we have r to the 2.5L. I don't think that's correct. I think one thing that we should hope to get is r to the L minus 1, because there exists a spectral algorithm that's able to achieve r to the L minus 1. So currently our result is actually worse than this simple spectral algorithm. Yeah, so I would guess r to the L minus 1 should be the correct result, but we were not able to achieve that.
Thank you. Any other questions?
Yeah, what is too homogeneous reparametrization?
Right. Sorry. So let me go to that part. Yeah. So that just refers to like the standard parametrization that we have, or the maybe the most straightforward parametrization for this tensor is going to be AI times UI tensor L, where AI is a constant and we optimize UI. So this is an L homogeneous parametrization because if I scale UI by a factor of lambda, then the component is scaled by a factor of lambda to the L. However, in our work, we actually use a different parametrization, which is in the red color. So we set the component as AI times CI to the power L minus 2 times UI tensor L, where AI is plus minus 1, and CI is fixed to be 1 over norm of UI. So if we use this parametrization, then if I multiply UI by a constant L, then the whole component is going to be multiplied by L squared because it is multiplied by, let's say lambda. By lambda, then the whole component is going to be multiplied by lambda squared because the UI tensor L part is going to grow by lambda to the L, but the CI to the L minus 2 part is going to decrease by lambda to the power L minus 2, and after things cancel, we get lambda squared. So that's why we call this a too homogeneous reparametrization.
Okay, thanks. Now, overfitting is usually not desired, but from your conclusions and open slide, over-parametrization is more desired. It has potential to help. So maybe generally over-parametrization is good or bad?
Right. Yeah, so that's a very good question. So over-parametrization can be both good and bad. The usual intuition is having over-parametrization allows optimization to be easier. For example, as I mentioned, if in this tensor problem, if we don't have over-parametrization, then it's going to get stuck even for orthogonal decomposable tensors, which we actually know how to solve using other algorithms. But if you over-parameterize, you will still find the same components, but you will, well, empirically for orthogonal tensors, you will find the same components, but you will not get stuck. So in that sense, over-parameterization can be beneficial. But of course, there's always a concern that over-parameterization leads to overfitting, and overfitting might lead to bad generalization, right? So for that, recently there are a lot of works that studies the generalization for interpolating models. By interpolating models, it's referred to the models that have zero training error. So I guess in many different settings, people were able to show that even if you have an interpolating model that has zero training loss, it's not necessarily bad for generalization. There are certainly cases where it is actually very bad for generalization, but there are also cases where it's not bad for generalization. And this is this tensor decomposition phenomena, since we are not working in the neurotangent kernel regime, is actually a setting where I believe generalization would be good, but it is true that our paper does not give generalization guarantees. It is known that if you are in the neurotangent kernel regime, then the generalization for this low rank tensor problem is not going to be good.